Welcome back to the Explainer. Today's Explainer is brought to you by Forge College. So, if you remember our previous lesson, Reflection, from node roles to RPC service patterns, we really got into the weeds on how your node deployment choices dictate your necessary RPC services. We saw how a validator, an RPC node, and an archival node each create completely different surface areas, right? Well, today we're going to take all of that synthesis and give it a real, structured vocabulary. We're introducing the core RPC patterns and the svm-client-architecture. We're basically taking those abstract ideas and turning them into a concrete, mechanical pattern blueprint for how these systems actually connect to one another.
Okay, let's dive into this master schematic. First up, we'll welcome you to the blueprint. Then, we'll tackle the three core mechanical RPC concepts: the pull for request and response, the push for streaming subscriptions, and the gauge for management endpoints. After that, we'll map these specific patterns to actual node roles and wrap it all up by building some highly resilient client workflows. Let's get to it.
Section 1. The pull. Request and response. Let's start with our very first mechanism here.
Now, I want you to visualize this not just as, boring lines of code, but as a physical, mechanical interaction inside a massive humming factory. Let's look at request and response. These are your synchronous JSON-RPC calls for discrete queries at a very specific moment in time. Think of something like getBalance. I want you to imagine a heavy mechanical pull cord lever. You walk right up to it, you pull the lever once, and exactly one piece of data pops out. Clunk. It's incredibly simple. From your client's perspective, it's super predictable, and it perfectly aligns with idempotent read operations. You ask a precise question about the state of the chain right now, and you get a precise answer. Boom. Done.
Section 2. The push. Streaming subscriptions. But what if you want more?
What if you don't just want one piece of data? What if you absolutely need to know every single time that data changes, but you really don't want to stand there yanking that pull cord 1,000 times a minute? Well, that brings us to our second mechanism, the subscription model. A subscription is a persistent WebSocket channel that pushes state changes to you over time. A great example of this is account subscribe. Instead of that pull cord, imagine you're turning on a massive industrial conveyor belt. You flip the switch just once, and this continuous asynchronous stream of widgets flows directly to you whenever a relevant change happens. It's fantastic because it beautifully reduces client polling overhead. But listen, there's a catch here. You are now responsible for that conveyor belt. You have to manage the entire connection lifecycle, handle reconnections if the power flickers, and somehow deal with the back pressure if those widgets start flying at you way too fast.
Section 3. The gauge. Management endpoints. Now, hold on a sec.
Before you start yanking levers and firing up these massive conveyor belts, you really need to make sure the factory isn't about to, explode. That leads us to our third mechanism, management endpoints. These provide vital operational metadata and health signals that are used primarily by orchestrators. Imagine a really fragile glass pressure gauge mounted on a thick industrial pipe. You literally tap the glass to check the pressure before you dare open the valve. These are very low bandwidth, but high importance signals. They tell you if the node is caught up, if it can actually accept traffic, or if it's dangerously overloaded. You've got to use these gauges as lightweight probes. Do not, under any circumstances, route your heavy user traffic through them. Now, what's really interesting here is how we can consolidate our entire toolkit. We've got our three mechanical patterns side by side. Row 1, request and response for single query, synchronous needs like getBalance. Row 2, subscriptions for continuous push updates like account subscribe. And row 3, management for operational health and metrics. This right here, this is your core vocabulary. When you choose a pattern, you are choosing your trade-offs. You want event-like updates from a pull cord? You're going to pay super high polling costs. You want push timeliness? You're going to have to take on all that connection complexity.
Section 4. Code walkthrough. Polling versus WebSockets. Let's take a look under the hood.
Let's see what these theoretical machines actually look like when we translate them into a minimal TypeScript client. First up, we've got polling. It uses an asynchronous loop with periodic HTTP requests. It's incredibly safe. If an error happens, you just catch it, wait a few seconds, and try pulling the cord again. But man, the overhead is high. Now contrast that with WebSockets. It's event-driven, it's snappy, it's responsive, but notice the sheer complexity here. You have to establish a persistent connection, listen for specific notification methods, and, critically, you have to write a handler for when the socket inevitably closes to trigger a reconnection. It's that classic engineering trade-off: high polling costs on one side versus gnarly connection management complexity on the other.
Section 5. Mapping patterns to nodes. So, we have the mechanics down.
The next logical question, and this ties right back to our previous lesson on node rules, is where exactly do we bolt these mechanisms onto our architecture? Well, whenever you're designing an SVM client architecture, you've got to follow these 4 engineering steps. Step 1. Classify your requirements. What's your exact latency tolerance? What's your query volume? Step 2. Assign patterns to roles. Route them based on actual storage and compute availability. Step 3. Design, discovery, and fallback. Make sure your client knows exactly what to do if an endpoint just goes dark. And Step 4. Instrument and monitor. Seriously, use those pressure gauges so you avoid sending heavy requests to an already overloaded node.
And this brilliantly illustrates what happens when you ignore those steps. Look at the humorously bad idea of hooking up thousands of heavy WebSocket conveyor belts directly to a validator. Guys, validators are incredibly busy participating in consensus. They are absolutely not sized for massive numbers of persistent user connections. If you do this, your system is going to be ridiculously fragile. On the flip side, we see the actual good idea, routing your pub/sub subscription workloads through a dedicated indexer node that precomputes events and handles the fan-out safely. Much better.
Let's quickly summarize those exact node-to-pattern assignment rules, because this is how you build a stable system. Archival nodes? They're heavy, so they get the historical queries. Dedicated RPC nodes are your frontline workers. Give them the high-throughput, low-latency request and response reads. Indexers and notification nodes? They manage the heavy lifting of your subscription workloads. And validators? You keep them completely clear for consensus. This deliberate mapping is a total game changer. It dramatically reduces your operational risk and makes capacity planning so much clearer.
Section 6. Building resilient client workflows. Because we all know things are going to break.
Seriously, even with perfect capacity planning, in any massive factory, machinery inevitably jams. The power flickers. Belts literally snap. So the crucial point here is operationalizing resilience straight into your client. First, implement conservative retries for your request and response calls. Use exponential backoff with a little jitter, so you don't accidentally DDoS the node that's just trying to recover. Second, build fallback flows. If your WebSocket subscription suddenly drops, instantly fall back to short interval polling so your user isn't left hanging in the dark. And third, the absolute golden rule. Implement integrity checks. When a WebSocket reconnects, you must query the latest state using a standard request and response method to make sure you didn't miss anything.
In fact, I want to leave you with this provocative question to ponder. If your continuous subscription drops right now, how will your specific client application dynamically recover its state without missing a single beat? Think about it. If you aren't doing an integrity check right upon reconnection, you are almost certainly losing data while that conveyor belt was turned off. No way around it.
So, to prepare for our next lesson on development workflows, I want you to take some time to annotate the actual endpoints your application uses. Label them as request response, subscription, or management, and map each one to the proper node role. Having this ready is going to make designing your local testing strategies a breeze. Before we go, ask yourself, when your connection inevitably drops today, will your client gracefully recover? Or will your users just be left staring at a broken conveyor belt? This explainer was made by Forge College. Please head over to forge.college to learn more about this subject and explore a ton of other fascinating Web3 topics. Thanks so much for watching and keep building.